In this video, we're going to be taking a look at different ways that we can prove triangles to be congruent. There's going to be three methods that we're going to learn. Um, just to review, remember in the last section we learned that two figures are considered congruent, two figures. So two triangles, two quadrilaterals, two pentagons, and so forth. Two figures are congruent if all the pairs of corresponding sides and corresponding angles are congruent. So if you were looking at two triangles and trying to decide if they were congruent, you would have to, by this definition, determine that you'd have to determine that there are three pairs of congruent sides and three pairs of congruent angles, according to what this definition says, right? Well, what we're going to learn in this section is that there are actually some shortcuts for proving that triangles are congruent. You don't have to necessarily determine that there are three pairs of sides and three pairs of angles that are congruent. There's going to be some shortcuts. So let's look at the first one. It's called the side-side-side congruence postulate, or postulate 12 in our textbook. The side-side-side congruence postulate is usually just abbreviated as SSS, standing for side-side-side. And what it says is that if three sides of one triangle are congruent to three sides of a second triangle, then the two triangles are congruent. So if you compare what this says to what this definition of congruent figures says, you'll notice that in the side-side-side congruence, we don't have to look at angles at all. If we can match up each of the sides of one triangle to a side of the other triangle and have those three pairs of sides alone, that's enough to determine that the triangles are congruent. So in this figure over here, if segment AC is congruent to segment QR, and if segment AB is congruent to segment SQ, and finally segment BC is congruent to segment RS, then triangle ABC would have to be congruent to triangle. Now I got to be careful, remember, with the letters that I'm using, the order of the letters. I went A, B, C. So point A, or vertex A, corresponds to vertex Q. So Q is the first one I'm going to put in the name of this triangle right here. In this triangle, I went from A then to B. So I'm going to go from Q to S. And then the last vertex is R. So triangle ABC would be congruent to triangle QSR in this figure here, according to the side-side-side congruence postulate. So if we're looking at this example down here, does the diagram give enough information to show that the triangles are congruent? In other words, can we apply the side-side-side postulate to this triangle? Well, if we start listing out the sides that are congruent, we know that XY is congruent to YZ, because you can see they have the same marks on them. We also know that XW is congruent to WZ, because of course they have the same marks. So sometimes what I'll do is as I'm listing out pairs of things that are congruent, I'll put a little S next to congruent pairs of sides, just to kind of remind myself that I have one, two of the pairs of sides that I need. But it looks like I'm missing the third one. So the temptation on this problem is to say, nope, there's not enough information because it only gives me two pairs of sides, and according to the postulate, I need three. But what you have to look out for on a lot of these problems are diagrams where the two triangles that you might be trying to prove congruent are sharing a part. For instance, you'll notice that they are both using segment YW right here. And we learned a while back about the reflexive property that says that everything is congruent to itself. So when we state that segment YW is congruent to itself, we are actually stating that one of the sides of the triangle on the left is congruent to the corresponding side of the triangle on the right. It's just that YW is a side of both triangles. So there's my third pair of sides. So I would say yes, triangle XYW is congruent to triangle, I got to go, if I went XYW, then I have to put the other triangle in this order, ZYW. So triangle XYW is congruent to triangle ZYW by side, side, side. So that's the side-side-side postulate. The next shortcut that we're going to learn is called the side-angle side. And it says that if two sides and the included angle, we're going to talk in a minute about what this means, included angle, but for now let's just look at the postulate. If two sides and the included angle of one triangle are congruent to two sides and the included angle of a second triangle, then the two triangles are congruent. So what does that mean? What does it mean for an angle to be the included angle? Well, if you notice over here, let's look at triangle PQR. We have this segment PQ and this segment PR that join at point P. And so angle P, the place where segment PQ and segment PR join together, that angle is considered the included angle between those two segments or those two sides. If I look at triangle XYW here, I notice that YW and XW, they intersect at point W right there. So angle W is the included angle for those particular two segments. If I was looking at XY and YW, then angle Y would be the included angle between XY and YW. Or if I was looking at YX and WX, then angle X would be the included angle. So that's what this phrase included angle refers to. It's the angle that's formed by two sides that join together. So to kind of see how the SAS postulate works for this diagram, we would say, okay, segment PQ is congruent to segment XW. We can just look at the marks on the segments. Segment PR is congruent to segment YW. And angle P, the included angle between PR and PQ, is congruent to angle W, the included angle between YW and XW. So that means by SSS that triangle QPR, I'll use that name, triangle QPR, is congruent to triangle, so in QPR, Q corresponds to X, and then P corresponds to W, and R corresponds to Y. So that's what would be true about this diagram because of the SAS postulate. So in this example, we want to look, does the diagram give enough information to use SAS? If so, write the congruence and explain your reasoning. So if I look at A, I see that AC as a segment is congruent to JI. That's one pair of sides. I see that segment BC is congruent to segment HJ. It's another pair of sides. And I see that I have a pair of angles, angle C congruent to angle J. That's a pair of angles. So I have the right letters. S, S, and A are two sides and an angle. So I just need to check, is the angle the right angle? Is it the included angle? I shouldn't say right angle. I guess I should say, is it the correct angle? Is it the included angle for the sides? So if I kind of color code some of these things, segment AC congruent to segment JI, segment BC congruent to segment HJ, and then I have angle C congruent to angle J. You'll notice that the colors, as I color coded that, which sometimes can help kind of visualize things, I notice that it matches up, right? I have an orange segment, kind of a purplish segment and a purplish segment, and then this pink segment, or I'm sorry, pink angle that's between the two of them, that's formed by those two sides. So that means that's the included angle. So yes, I can say that triangle ABC is congruent to triangle ABC, so I'd have to go IHJ by SAS. Now if I look over here at example B, you'll notice that I have segment ON congruent to segment XW. Oops, I forgot to put my congruent sign in there. So there's one pair of sides. I have segment MN congruent to segment XY. It's another pair of sides. And I have angle O that's congruent to angle W. So again, two sides and an angle, but is it the included angle? Well, no, it's not, right? If I look at YX, I'll color code again. YX congruent to MN, and I have XW congruent to NO, and then I have angle W and angle O. You can see my angle is not the angle that's formed by the two segments that I've kind of color coded. So it's not the included angle. So no, because the angles are not included angles. I guess that could be our explanation there. Even though I have two pairs of sides and one pair of angles, it's not the included angles. So SAS doesn't work there. Now we have a third shortcut. It's called angle side angle. And it says this: if two angles in the included side of one triangle are congruent to two angles in the included side of another triangle, then the two triangles are congruent. We see this word included again. And this time we're talking about an included side, not an included angle. So what do we mean by included side? Well, if you notice here on triangle ABC, I have angle A marked and I have angle B marked. And then I have segment AB marked as congruent to a segment over here. So segment AB, it joins the vertices of the two angles that I'm looking at, angle A and angle B. So a segment that joins the vertices of two angles is considered the included side of a triangle. So, for instance, BC would be the included side between angle B and angle C because it's joining those two vertices. So that's what included side means. So over here in this diagram we have angle A congruent to angle D. We have angle B congruent to angle F. And we have segment AB congruent to segment FD. So that means that we can say triangle ABC is congruent to triangle, see, A matches up with D, B matches up with F, and C matches up with E. So triangle ABC is congruent to triangle DFE. So looking at example 3 down here, does ASA work? So on part A, I have two right angles that are congruent. Angle A congruent to angle D, pair of angles. I have angle B congruent to angle E, another pair of angles. And I have a segment AB that's congruent to another segment ED. So I have a pair of sides. So I have two A's and an S, just like it looks like I need for ASA. Is it the right side? Is it the included side between these two angles? In other words, is it the included side for angles A and B? Well, yeah, because segment AB joins the vertices of angles A and B. And ED joins the vertices of angles E and D. So that is an included side. So yes, triangle ABC is congruent to triangle A corresponds to D, B corresponds to E, and C corresponds to F by angle, side, angle. So looking over here, we have angle G congruent to angle M, and I have angle J congruent to angle K, and I have segment HI congruent to segment KM. So I have two pairs of angles and a pair of sides. And if I even look at the triangle on the right here, triangle KLM, the side is joining the vertices of the two angles, right? Segment KM joins the vertices of angle K and angle M. But segment HI does not join the vertices of angle Q and J. It doesn't connect G to J. So we have to say here no, because HI is not the included side for angle G and angle J. So ASA does not work in this example. All right, so the last couple things that you might have on your note sheet are a couple of proofs. Example 4 is a proof, and example 5 is a proof. I'm going to do those in a separate video. So for now, this is all we're looking at. We have ASA, we have SAS, and we have SSS as three kind of shortcuts, if you will, for proving that triangles are congruent. They bypass this longer definition of congruent figures where you have to match up three pairs of angles and three pairs of sides. In a way, they're shortcuts to show that two triangles would be congruent. All right, so we'll see you next time.